Okay, so you have binary star. So say you had a blue one. Whoop. I'm going to do 4 of these guys. Whoop. It's the same star. Can't bother making them the same size. Whoop. Okay, and then you've got the red star. So let's here have it there, and then there. Doo doo, and then this is behind. So just rub this out a little bit. So now it's behind. Yep. Okay, so and you've got a light curve, and it looks sort of like this in all of the filters, and then the secondary. So that's just straight color. But if you thought about what kind of color this light was as it went along, you see when the red star blocks some of the blue stuff, then it'll become redder overall, and when the blue star blocks the red star, it'll become bluer overall. So you'd get something like this, I guess. Where up would be red and down would be blue. And the way that you kind of look at this color change is B minus V, or it could be any of the different filters. They're all colors. So what's the difference between the bluer filter and a redder filter? Now the most sensitive one to temperature, which is what causes the color, is B minus V. So that's why you get B minus V images, because the temperature is most sensitive there, the temperature change. Now, at the moment you have your light curves. Oop. Try it again. This is the most laziest way to do it. And you've got phase on the x-axis, which is fine, that's correct. And on the y-axis you have instrumental magnitude. Now what that means is like you as yet haven't made it calibrated. It's not an apparent magnitude, which means it's on the actual observational scale. What your instrumental magnitude just is the difference between a comparison and the binary. And which is fine. And if you're just looking at the changes, then that's perfectly fine. If you're not actually worried about the actual brightness in B or V or R or I, that's fine. You just go, oh yep, there's an eclipse, it's a binary, and then that's what you know about it. And to some extent, to the same extent, you could have instrumental color change, and have the thing that was on the other screen like that, and you could have the y-axis in instrumental, so that'd be the instrumental of B minus the instrumental of V, poorly drawn, but that's instrumental. So if you can actually convert your light curve from instrumental magnitude into actual magnitude, then you can actually calculate the temperature from these colors. It's not quite so straightforward, but it sort of is. At the moment, you can look at the color change on this arbitrary scale and know that it changes, but you won't be able to use it to calculate actual temperatures or anything like that. So if you can plot B minus V versus phase, you'll probably get that. But the y-axis will be on an arbitrary scaling. So you're looking at the change, which is great, but it's not telling you something absolute. So what you need to do is you have your comparison star and your eclipsing binary, and this has, just for example, 15.6 is the known VB magnitude, and 14.8 is the known V magnitude. And over here, all you know is the difference between the comparison and the variable. So you know how much brighter or dimmer the variable is than this known comparison. So here B and you don't actually know them. And because you do comp, I always get this around the wrong way, so you'll have sign errors. Comp minus variable, so that's what you're plotting. If you have comp minus variable, so let's put that in brackets, that's the measurements you've got so far. So you got the difference. So if you add the comp known, then that is the variable known. You see? Because, see, that's what I mean. Got to watch me and my signs. I always get them out. So, no, minus comp. Watch your signs, that's all I'm saying. So comp minus variable, whichever way around that is. Watch your signs. And then you compare it to the known values, then you get the known variable values. So it's probably a better way of writing that. Variable minus comp plus comp equals, yeah, variable. That's better. So you just, essentially all that means is you add the known B or known V to your data. That's it. As always, there's a longer story and you can do things more complicated, but that will get you firmly in the ballpark of the actual brightness of your star. Of course, you don't need to do that just to see that the color is changing. You can see that on an arbitrary scale already, but to actually get the values of how bright it is in B and how bright it is in V, no, you need to do that. So here I've got Aladdin, which I think you've used before, and you type in your coordinates and stuff to bring something up. And here's your preview image, which I'm sure you fiddle around with. On the left here, you have a whole bunch of stuff which connects out to image servers and photometric servers and data blah. Astronomy has a lot of interconnected data sets. So you want to know what your comparison star magnitude is. So that's RLRA, just a star I look at every now and then. I'm going to pick this star as our comparison star. And I'm going to see over here, catalog. Visor is where all the catalogs are kept in astronomy. It's an online thing, and they've sorted out all of the catalogs into what they are, miscellaneous being obviously the most useful, but photometric data, so this will give you measurements of photometry. So it'll give you your magnitudes and stuff. You open it up, I think the color code is, yeah, in view, so it's in this catalog has measurements of this view and orange doesn't. So to get B and V, you should have a look through and see what's in all of them. But to get B and V, AAVSO APAS is the latest one. So we'll load that up. There we go. So slide over there, and we've selected the dot, and you go across RA-DEC error in that field. So B minus V, and well, that's the color already. So Vmag and Bmag. There you go. They're your errors. You want to keep your errors because that's how well APAS thinks it knows what the value is. So that's how you get B and V. Now you might get R and I if you're lucky. Yes, so A pass will have R and I. So hopefully your stars are in A pass. They should be. If they're not in DR9, we can go another route to get the values from DR8 or DR7, but you may be able to find values elsewhere. So R and I, the ones you're using, tend to be in SDSS. So if SDSS is around here, it should be all. No, it's actually, this field's not in SDSS for some reason, but you might want to check Pan Stars might have something. Have a look, see what you get. So this catalog here is UBV in it. So yeah, have a look through and try and find the BV, R, and I. And there we go. So that's how you get those values. Ooh, wow. Sorry. There's an R. G. Interesting. Anyway, so there's lots of explores. You can go down multiple rabbit holes. But that gives you um, the actual calibrated magnitude of your variable stars. So, and that's 12 minutes. So that's quite a bit so far. But basically, I've just done a search B minus V temperature, and all of these things turn up. Like, it's a very well known relationship. Yeah, you might want to watch that video. I don't know if it's any good. But you see color index and temperature conversion. So here's an article, a study of the color temperature relation. That's actual top of the field journal article about it. There's the Wikipedia. So here you have B minus V. And then there's the temperature. So all different types of stars. They have all, negative is very blue, positive is red. And red is normal stars are about 2, and that's about as blue as stars get. So you can see you can make colors in other relationships as well, but B minus V is the traditional one. This looks like a pretty good Wikipedia article. I can talk about that at some other time. Here's another thing. I think that's the same article as before. Some relationships to calculate the temperature from the B minus V, etc. 1968. Very interesting. So that gives you an idea about how to get the temperature, but the thing about eclipsing binaries is it's a complex system. So let me just get my squiggly thing back up. So the light curve is a combination of the geometry, the temperature, shape, and all sorts of things. So eventually you're going to, once you got it in that calibrated form, we're going to put it into a modeling program. This is the program. You might want to install it and see if you can install it for beginning. Once you've got the calibrated light curves, we're going to bring it into this program. And I just got some Google image search. I'm pretty sure I've mentioned it before. You have your data, and then you have the light curve it tries to fit. So here's a kind of example. So this is a bit blurry, but the blue dots, which is a noisy kind of, that's the light curve, and you can't really see it, but there is a straight line which is representing the model as it goes through. And here we go. Well, here's an example. If you've got this is very idyllic. I think this is just a super clean example. You have the B and the V light curve, and here's radial velocity, which we don't have. You don't necessarily need it. We do need it to get the absolute mass, but then it draws a model for you as well. Is there any other kind of things? Use that guy. I don't know. Yeah. It gives you output. I'm not seeing any useful. Here someone's got UBVRI. That all of the. Yeah. Here's another. Here's what I tried to draw on my. On my thing. So you're going to take your light curves and hopefully you get a model like this out. Except yours will be, closer together and kind of donutty shape, I assume. Well, the very short period one is. Ooh, that's a really interesting one. See, and there's one with a spot. All sorts of exciting stuff. So that's basically it. Once you've got the light curves in the calibrated form, you can start modeling it.